Welcome to ScaleDojo.dev. In this video, we are going to design a scalable notification system. Now, notification systems are everywhere, right? Whenever you receive an email from Amazon, an OTP from your bank, a password reset link, or a push notification from Instagram, there is a notification system working behind the scenes. The challenge is that millions of users may trigger notifications simultaneously. We need a system that is fast, scalable, reliable, and fault tolerant. Let us see how this architecture solves that problem. Now, before going to the actual architecture, let us go through the design specifications. First, we have the functional requirements like send, push, SMS, and email, and then support retries on failure. Then we have non-functional requirements like handle 10 million daily alerts, zero data loss, less than 300 millisecond latency. Then we have constraints like deliveries must be asynchronous. We have a budget limit of $24 per hour. And then we have capacity estimation, which is 10 million alerts per day, 116 alerts per second, 3 channels per alert. So it gives approximation of 350 deliveries per second and queue depth of 10K during spikes. Now, the key trade-off is at least one versus exactly one's delivery, which is simplicity versus delivery guarantees. Now, let us start building the architecture. First, let's start from the very top. We have a client. Now, the user or client application wants to send a notification. For example, imagine a user places an order on an e-commerce website. The application now wants to send an order confirmation. Now, instead of directly contacting an email provider, the client first sends an HTTP request to the API gateway. So the next one which comes in picture is the API gateway. The API gateway acts as the single entry point into our system. Every request first passes through this component. The gateway performs several important tasks. It authenticates the request, checks authorization, performs rate limiting to prevent abuse, and routes the request to one of the available notification API instances. Since we have multiple notification API instances running, the gateway can distribute the incoming traffic among them, allowing horizontal scaling. This prevents any single server from becoming overloaded. Now we have the notification API instances. So the request reaches the notification API. Notice that there are two instances in this service. This allows us to handle much higher traffic by simply adding more servers. We can add even more instances, but we have a budget constraint to keep in mind. The notification API validates the incoming request. It checks whether all required fields are present, verifies the notification type is valid, and creates a notification event. An important thing to understand here is that the notification API does not actually send the emails or the SMS messages. If it tried to contact external email providers directly, the client would have to wait several seconds before receiving a response. Instead, the API publishes the notification to Kafka, also known as the notification queue. So next in picture comes the notification queue. So now we have the notification queue. Immediately after publishing the message from server to queue, the server returns a success response to the client. This keeps API latency extremely low. Now coming to the notification queue, it is one of the most important components in this architecture. Here, let's say we are using Kafka. Kafka acts as a buffer between the notification API and the workers. Instead of processing notifications immediately, we simply store them inside the queue. This provides several benefits, like firstly, producers and consumers become completely independent. Second, traffic spikes are absorbed by the queue instead of overwhelming downstream services. Like imagine a Black Friday sale where 1 million notifications arrive in just a few seconds. The notification APIs continue publishing messages into Kafka while workers process them at their own speed. Nothing gets lost. The queue also improves fault tolerance because messages remain stored until they're successfully processed. Now we have a delivery worker. Now the delivery worker begins consuming messages from Kafka. These workers perform heavy processing. For every notification, a worker determines what type of notification needs to be sent. For example, it may be an email, SMS, or a push notification. If traffic increases, we simply launch more workers. Since workers operate independently, this allows the system to scale horizontally without changing any other component. And if a worker crashes, another worker can continue processing the remaining messages from Kafka. Now, after processing the message, the worker forwards it to the notification service. Think of it as an abstraction layer over internal notification providers. Instead of workers communicating directly with the services like SendGrid, Twilio, Amazon SES, etc., they only communicate with the notification service. Based on the type of notification, the service selects the correct provider. This keeps our architecture modular. And if we decide to change providers in future, we only modify this layer rather than updating every worker. We also have a cache memory which is connected to the delivery worker. The cache stores frequently accessed data, so we do not have to repeatedly query the database. For example, it may store user notification preferences, notification templates, delivery status, or provider configuration. Whenever this information is already available in the cache, we can retrieve it much faster than accessing the database. This reduces latency and lowers the database load. We also must have a main permanent database. Therefore, we have a notification log which is connected to the delivery worker. Every notification is recorded inside the notification log database. This database stores important information notifications such as notification ID, recipient, notification type, current status, and many more. Keeping this history is useful for auditing, analytics, customer support, and other aspects, allowing users to view their previous notifications. We also must have something known as a dead later queue in our system, and it is very important. This is because sometimes notification may fail repeatedly. For example, an email address may be invalid, a third party provider may reject the request, or the message itself may be malformed. Instead of retrying forever, the system retries for a fixed number of times, and if all the retries fail, the notification is moved into a dead later queue. This prevents problematic messages from blocking the normal processing pipeline. Engineers can later inspect these failed messages, identify the root cause, and replay them if necessary. At last, we have a monitoring and alerting system. No production system is complete without monitoring. The monitoring and alerting service continuously tracks the system health. It monitors API latency, queue size, worker failures, etc. So this monitoring system can be connected to our servers, various workers that we have in our architecture, and many more. Observability is extremely important in large distributed systems. So this is the complete notification system architecture, and let's summarize the complete flow. A client sends a notification request to the API gateway. The API gateway authenticates the request and forwards it to one of the notification API instances. The notification API validates the request and publishes a notification event to Kafka. Kafka stores the event until a delivery worker consumes it. The worker processes the notification and forwards it to the notification service. And now the notification service delivers the notification using the appropriate provider. The delivery result is stored in the notification log database. Frequently accessed information is cached for faster access. Monitoring continuously tracks system health, and if a notification repeatedly fails, even after retries, it is moved to the dead later queue. Now we can run our architecture, and we can see that it got a perfect score because we met all the requirements that we were needed to meet. Now, we need to note that we can build an even more complicated or a scaled up architecture as compared to this that we have right here. But since here we had a budget constraint of $24 per hour, therefore keeping that budget constraint in mind, this is the most optimal architecture that we derived. We can also run our architecture in Murphy's lab to see its overall performance. And when we exit Murphy's lab, we get a report of its performance. So this is the basic system design for a notification system.